All right, thank you for joining. Welcome to the Advances in Forest Monitoring Alert Systems webinar. My name is Alice Gottesman, and I'm an engagement specialist with Global Forest Watch. Today's webinar will be focused on the forest monitoring alert systems available on Global Forest Watch, including 2 new systems. And this webinar is part of a mini series. We're planning a second webinar for this summer focused on how to access and investigate these alerts using Global Forest Watch. So before we get started, I wanted to give a quick explainer of how you can ask us questions. If you have a question throughout the presentation, please enter it through the Q&A button. At the end of the presentation, we'll have some time to answer your questions. We'll also be sharing a recording of this webinar as well as a copy of the presentation within the next few business days. And at the end of this webinar, a survey should populate on your screen where you can share any feedback you might have for us on our tools, on our data, or on our webinar. And we'd really appreciate hearing any feedback you might have. Today's speakers include Michaela Weiss of Global Forest Watch, Dr. Johannes Reiche of Wageningen, Amy Pickens of UMD GLAD. Michaela leads Global Forest Watch's strategy and partnerships for satellite-based forest monitoring. She has a particular interest in on-the-ground use of early warning deforestation systems and leads Global Forest Watch's engagement with law enforcement. Johannes is Assistant Professor of Radar Remote Sensing at the Laboratory of Geoinformation Science and Remote Sensing at Wageningen University. His research interest is on utilizing radar remote sensing to unravel human activities in and dynamics of forest ecosystems, with a strong focus on multi-sensor methods and near real-time change monitoring. Amy is a remote sensing scientist in the Global Land Analysis and Discovery Lab at the University of Maryland. She maintains the GLAD Landsat Alerts and is developing the Sentinel-2 alerts for near real-time forest loss monitoring. She also evaluates global water dynamics and other land cover and land use changes. The goal of today's webinar is to provide an overview of forest monitoring alert systems available in Global Forest Watch. And this includes what they measure as well as how they can be used. The alert systems that we'll talk about include radar for detecting deforestation alerts or RADD alerts, GLAD alert systems, and Viirs active fire alerts. And as stated earlier, another webinar is being planned for the summer to focus on how you can then access and investigate these alert systems using Global Forest Watch. So first, I'll provide a quick overview of what Global Forest Watch is. Global Forest Watch offers an integrated, openly accessible suite of tools designed to enable experts and non-experts alike to access information about forest change and mobilize action. And some high-level examples of how this is done include increasing knowledge and transparency about forest landscapes. Global Forest Watch tools and data offer access to the state of the world's forests to everyone, everywhere for free. Harnessing information to mobilize local action by governments and civil society. We have a variety of partners in some programs that help promote data-driven action. And lastly, advancing private sector action to stop commodity-driven deforestation and manage forests sustainably. One of our tools, Global Forest Watch Pro, allow the private sector to measure risk associated with their supply chains. And these forest monitoring alert systems align with this strategy by allowing actors to identify likely forest change in near real time. And these different alerts can be used for a range of purposes. This infographic helps us illustrate how they've been used in the past in Peru. So the first pillar focuses on managing protected areas. So organizations like the Peruvian Protected Areas Service use deforestation alerts to monitor forests across the protected area system and allocate resources where they're most needed. And managers of individual protected areas use deforestation alerts to identify threats, prioritize patrolling activities, and coordinate actions with local stakeholders. The second pillar focuses on asserting community rights. Indigenous communities like Nuevo Saposoa and Patria Nueva use deforestation alerts to find potential invasions to their territories and plan patrols and follow-up investigations by the authorities. The third pillar focuses on investigating illegal activities. Authorities like the Environmental Prosecutor's Office use deforestation alerts to identify potential illegal activity and confirm other evidence in legal cases. The fourth pillar focuses on enforcing conservation agreements. The Forest Oversight Agency implements a program in which communities pay fines for forest management violations by conserving a portion of their forests. They use deforestation alerts to identify conservation areas and monitor compliance with the commitments. And the fifth and last pillar focuses on raising public awareness. Groups like Amazon Conservation use deforestation alerts to publish online reports about recent deforestation in the Peruvian Amazon in order to raise public awareness. So this is just one example of how deforestation alerts have been used in Peru. In 2017, Rainforest Foundation US began supporting the community monitors in Peru in monitoring and verifying deforestation in their respective indigenous communities through the use of GLAD alerts and the Forest Watcher mobile application, leading to the discovery, investigation, and halt of a large illegal coca farm. Over time, this project built a bridge to more formalized coordination among civil society, indigenous organizations, and the government in Peru for ongoing and future activities to protect against forest threats. The tools continue to be used during the pandemic to deliver and act on evidence gathered in the field where it's almost impossible for authorities to investigate. And this is an advancement that the Rainforest Foundation US noted will ideally change the paradigm moving forward with regards to remote forest monitoring. This is just one example of many great efforts by various organizations and communities around the world. So the detailed, frequently updated deforestation alerts, such as the weekly GLAD-L alerts from UMD GLAD, have proven valuable for supply chain monitoring, law enforcement, and community monitoring. Here you can see an example of what the GLAD-L deforestation alerts show. They're indicating a new logging road entering a national park buffer zone in Peru. However, in the humid tropics where Global Forest Watch often works, cloud cover can be a persistent problem. As a result, deforestation may be detected months after it occurs and cause problems for users, such as companies being unfairly called out for deforestation that happened and was addressed months prior. And as a result, we've worked with our partners, Wageningen and UMD GLAD, to develop two new complementary alert systems. The new GLAD S2 alerts detect forest disturbances across the Amazon basin in greater detail than ever before. The alerts are based on the European Space Agency's Sentinel-2 satellite program and developed by UMD GLAD. The GLAD S2 alerts offer much more detail than the GLAD-L alerts due to their higher resolution and more frequent return times, meaning that they not only pick up change faster, but they also have a better chance of getting a cloud-free image. Amy will expand on both of the GLAD alert systems shortly. The radar for detecting deforestation, or RADD alerts, detect forest change disturbances, rain or shine, using satellite-based radar data. Radar data can see through clouds, meaning that the long wavelengths of radar can pierce through cloud cover and return data when optical sensors cannot. With the European Space Agency's new Sentinel-1 satellite, freely available radar data is available for the globe for the first time ever. So we worked with Wageningen and Satelligence to create a radar deforestation system using Sentinel-1 data to address coverage gaps due to cloud cover. Johannes will expand on the RADD alert system a bit later on. So we're now working on integrating these alert systems on Global Forest Watch. And rather than thinking of them as competing systems, try to think of them as complementary. So if two of these alert systems detect change in the same location, this gives us confidence that something is actually happening. And having 3 different alert systems allows us to pick up and confirm changes faster than any one of them alone. So during the webinar, we'll provide an overview of the GLAD, RADD, and Viirs alert systems, including what they measure and how they can be used. We'll then summarize how each alert system can be used and indicate where they can be accessed. At the end of the presentation, we'll provide ample time for questions. So if you have a question during the presentation, please enter it into the Q&A. I'll now pass it over to Amy to discuss the GLAD alert systems.
All right. Thank you, Alice. All right, cool. So like Alice said, hold on, a little bit of trouble here. I'm Amy sorry, it's got a little delay. Amy Pickens from University of Maryland in the GLAD lab, and so yeah, I'll go over the two early warning systems that the GLAD operates now: the Landsat that's been going for a while, and the new Sentinel 2 alerts. And then after me, Johannes will go over the RADD alerts. And all three of these systems have a lot in common. So they all are near real-time systems that are mapping forest disturbance and define that as complete or partial loss of tree cover within a pixel. And they map all kinds of forest disturbance and don't separate between human and natural causes. So they'll capture logging as well as storm events. And they all employ the same basic steps of creating historical satellite image metrics that show the previous forest condition. And then for every new image that comes in, pre-processing that so that then we can apply the forest disturbance detection algorithm and can build confidence with the time series. And the differences and limitations between these three different systems stem largely from differences in the satellite data characteristics themselves. And so, all right. So here the GLAD L, and this formerly was just the GLAD alerts. So these are the Landsat alerts, and the GLAD S2, which are the Sentinel alerts. And the Landsat alerts are pan-tropical. They were first released in 2016 and have expanded to pan-tropical in 2018. And the Sentinel 2 were just made available on GFW, on Global Forest Watch, and cover only the Amazon basin right now. But we are going to expand it pan-tropically. So if you're not in the Amazon, stay tuned. But both of these are designed to identify forest disturbances as rapidly as possible in order to aid those protecting the forest on the ground. And they're not designed for area estimation. So that's just good to keep in mind as we go through this. But both of them are derived from satellite data. So Landsat is, the first alerts are from Landsat 7 and 8. And these are satellites that are continuously orbiting the Earth and photographing it and has 30-meter pixels and images everywhere, at best every 8 days, but it's often a bit longer. Sentinel 2, again, there's two satellites, A and B, and we have 10-meter pixels now, and it images everywhere every 5 days. And here's an example of what that looks like for a 5-day period in April. You can see that Sentinel 2 has complete coverage, whereas the Landsat covers a lot of it, but it's going to take several more days in order to cover it completely. And in both of these, one thing that immediately stands out is there's a lot of cloud cover. And so we can only apply the disturbance alert where we actually can see the ground. But we can take all of the ground observations between the clouds and apply the alert there. And we can also composite those together to get these regional images of the last clear ground observation. And so the Landsat alerts are 30 north to 30 south and detect loss within both primary and secondary forests that haven't had loss since 2014. Whereas the Sentinel alerts are only within the primary humid tropical forest of the Amazon basin. So both of these, right, are built on satellite image data using optical satellites, and these continuously orbiting, taking pictures, but not with your standard camera. They have a lot more bands. So this first one on the left here is a true color image. This is what it would look like if you're flying over in an airplane and looked out the window. And that comes from these 3 bands here in the visual spectrum. So it's same as the cones in our eyes, the red, green, and blue. But it also can capture in these much longer wavelengths, and that's where we get these kind of funny colored images over here. And this is really helpful because there's a big difference in how things reflect in the longer wavelengths, as you can also see here. And having these longer wavelengths enables us to better distinguish between different land covers and better be able to detect when there is a forest disturbance. And the Landsat is very similar. It also has a couple thermal bands, which are helpful for identifying clouds, which is a really critical step in early warning systems, well, optical early warning systems. And then radar is even much longer wavelengths. So the first step is to create historical satellite image metrics that show the previous forest condition. So here we're looking in Rondonia, and take all of the previous images that were collected over the previous 2 years and rank the reflectance values to then get these statistical metrics from the image bands, as well as ratios between pairs of bands. Like we can see in this one here, this is the ratio between the shortwave and the near infrared. So some of these longer wavelengths. And then it's the average between the 10th and the 25th once these have been ranked. And so this may sound kind of jargony, but in the end, right, the forest is this lighter color and the clearings are dark. And we create 72 of these metrics, and all of these help identify different aspects of the previous forest condition. And so that's the first step. And once we have this, then we can pre-process each new image. And so we get a new image like this one. And so, right, this was the middle image of that when I was showing the different ways of viewing satellite data. The forest is green, the pink is then cleared ground. And you can see there's these clouds blocking it. And so our first step is to identify where is the land, water, cloud, shadow, or haze with classification trees that use all of the bands and ratios between every pair of bands. And these classification trees are simply a model that's been trained to identify these different categories. And then we can apply automatically to then get the land, which is where we'll then apply the forest disturbance algorithm. And so here is just the land pixels left. And these are again classification trees for the disturbance algorithm, and use the data from the current image as well as from the historical metrics. So this is the same one I showed before, as well as then the differences between them. So here's the difference between that metric and what it is in the current image. And you can see now that all these new clearings show up in bright red. You can see this big patch of logging. Here's an old logging road, and then a bit of blue here that's showing recovery of the logging sites. So those recover more quickly than the logging road itself. And this then results in a yes or no forest disturbance label that then we can keep track of through time. And so the Sentinel alerts apply this only within the primary humid forest, whereas the Landsat alerts within both primary and secondary. So here's that current image, and then the difference, and then here's then the loss that's detected, or the disturbance that's detected. And so this is everywhere that's been disturbed up to this point in 2020. This was an image from October. And so then we assign the date from the first image it was first detected in. And then we build confidence with the time series. And with both systems, it's very similar. Every new alert is labeled as a single detection. And then the images after that either build confidence or take it away, right? So the idea is that if we have a false detection, it's often from an issue with cloud or haze that got through, or some other kind of image oddity. And it's unlikely that that's going to happen in the same place over and over again. And so if there's another loss within the next few images, there's a good chance that it is actually a real change. And so in the single detection is that, then the most kind of uncertain stage, but we want to release that to you as soon as possible so that you can act on it if it is real. And so for Landsat, it's if within the next 4 observations there's another force disturbance, then it moves to high confidence. Otherwise, it's deleted. And similarly with the Sentinel-2, it's then instead of 4, it's 3. But that's very similar. In the GLAD app, we also then divide this into a few more confidence levels, so that if you see red, and that's if it's been detected as loss at least 3 times in a row, you can have a lot of confidence that is a real loss. And all of these also, with these kind of where we also have some no, those also are typically lost. You'll see it more in the logging dynamics, but this is just to kind of continue to give more evidence to what's going on. And the time series is really helpful for this. But what's also really helpful is if you can actually look at it. So if you can pull it up on your computer or on your phone, and if you see a big clearing like this and has nice edges, you can be pretty sure that that's a real clearing. Or if you see a logging road snaking through, and you can also then know what kind of disturbance it is. And it's even better if you can look at the satellite imagery and see from it, you could see, if there is a bit of a cloud or something. But so this is the best way of going forward, but the time series is really, really helpful in that too. And it's something that we can automate a lot more. So here's the Sentinel alerts in Peru. You can see some logging roads, a lot of logging around the roads, some smallholder clearings. And here's how it compares with the Landsat. So most of the clearings are detected in both. Some of this is a timing issue of the most recent alerts. The logging roads are also picked up pretty well by both products, more complete with the Sentinel. But the Sentinel picks up a lot more of the individual logging sites. We also track it through time. So here you can see, so this is all the alerts from 2019 through current, and you can see earlier logging, and then it goes through time, and we see some newer logging action in some of these places, as well as a range of time of clearings. And we can also compare this with the Landsat for the areas that had agreement. So all the areas that were in white here, we can then compare the date of detection. And so here in blue are the places that Sentinel-2 was detected before Landsat, and red is where Landsat detected first. So you can see more often Sentinel-2 detects first, but sometimes Landsat does. And so really the fastest way is to look at them in combination. Some of the GFW team found that on average, Sentinel-2 in Peru detected alerts 11 days faster than the Landsat, and during the wet season, that was over 30 days. So the higher frequency of observation really does help, and particularly also when we think about the prevalence of cloud cover. So then zooming into the region down here, here's a zoom in of this logging with Sentinel and with Landsat. So right, you can see it's mostly just the logging roads, and yet while you don't see all the logging sites, this gives you enough information to know that logging is happening, that something's happening, and if something shouldn't be happening in this area, to go check it out. And to further kind of highlight the differences here between resolutions, here's a 30-meter pixel centered over a tree. And so if this tree was cleared, we would anticipate that the alert would be able to capture it. However, if the pixels are shifted and only it's split between several pixels, it's much less likely for it to be detected. But the Sentinel pixels, which here are all these little ones are Sentinel, it's even if if this tree is taken out, it's going to cover some Sentinel pixels. And so the Sentinel alert is much more sensitive to partial canopy removal, both from logging, from fire, from high wind storms. And this may be helpful or not, depending on your application. But certainly for logging, it makes a big difference. So here's Sentinel and Landsat, much coarser. And there's actually a few logging that happened right in this forest here that was detected by the alert. So more examples of what the alert captures. Here are some large fires in 2020 in Bolivia. And then you can see the burn scars that are left behind. And this is the latest observation. Here is frontier clearing in Colombia that is on the edge and also going into one of their national parks. And so the alert also captures these large clearings quite well. And here you can see the last observation. Also, here's a storm event where these trees got blown down. This one's a little harder to see in this image, but it's a bit pinker here. So all kinds of natural and human disturbances are captured. So just be aware of that as you use it. And here's a couple more examples. So this is some older examples, but from a flight that Peru's Ministry of Environment took and shared their photos with us. So here's a small clearing that's then this little red dot. Or large scale mining is obviously captured that just chews up the landscape. Or here's another small clearing that's then this little red dot. Or here's an example of what the storm event looks like. So this is why it's captured, because yeah, the tree canopy is broken down. So yeah, be aware of these things. And yeah, here's an example of the rapid expansion of logging in 2020 in Peru. So this is from July 14th. You can see there's not logging roads here. And then in 5 days, you get all of this logging road. And then 15 or 10 more days, you get all of this, and you can start to see a patchwork of logging sites. 5 more days. And it continues expanding as these roads just cut across and a whole patchwork of sites that are hard to see here. I agree. But so then here's the last clear image we get from 2020. And you can see this huge system of roads that was built in 3.5 months and tons of trees taken out compared to the original image. And then here's it in recovery. So this is early April. And then the last image we've gotten is that we can actually see the ground is from the end of April. And yeah, there's starting to be a lot of recovery of the sites individual tree sites. And here's then the progression through time as mapped by the alerts and all of the alerts that were captured along with their confidence levels. So certainly there is a lot more logging that's happening here, but the alerts do capture a lot of the large trees that have been removed. And here's the last observation, which in some cases can be kind of messy, like we see here. So when we think about the strengths, limitations, and next steps, it is really exciting, these Sentinel-2 alerts with the 10-meter pixels. They enable much greater detection of logging and other small clearings. And since we get a new image every 5 days, we're able to see things much faster and able to see more often, which is also helpful when you've got quick canopy closure. Yeah, more opportunities to see when there's not cloud cover. So for both of these reasons, it's a really cool new system. But yeah, there's also, of course, limitations. So this cloud cover, persistent cloud cover can obscure parts of the forest for weeks to months, particularly during the wet season. And one thing that I didn't put here, but could be an advantage or disadvantage, is that there is more partial canopy removal detected from storms, fires, logging. And so some of these can be really helpful, but others you may want or may not want. And the accuracy has not yet been statistically assessed for this. So as we pan around, it looks pretty good, but it hasn't actually been evaluated. There are some false detections due to poor cloud or haze masking, where it can where it's not taken out and then it makes it into the stage where we apply the forest disturbance detection algorithm, and that can cause a false alert. But we are currently improving these models and have seen great improvements in that, and so we'll soon apply those new models of cloud, haze, and shadow detection to the alert, and will improve the quality of the forest disturbance alert as well. And for those of you who aren't in the Amazon, stay tuned. We are going to expand to pan-tropical, just as with the Landsat alert. And yeah, it's really exciting to see where this will go and how it'll be used. And so yeah, we'd all love to hear your stories as you do use it. So you can access the data through Global Forest Watch. You'll hear more about that. You can also access it through, GLAD has a couple web apps, one for Sentinel-2 and one for Landsat. And these give you a richer way of visualizing the alerts and auxiliary data and looking at the satellite data that goes into it, as well as then you can get a tiled data download in raster format. And you can also access them on Earth Engine. So just a shout out for the Sentinel-2 app. Here it is. You can click on any pixel and you'll get a thumbnail of the image in which it was detected, as well as the date. And so that's helpful in seeing what's going on with the alert. You also can look at all these different layers that I showed today. You can look at the Landsat alerts or see the map biomas alert from 2019 or primary forest. You can also look at different base images. This select date to view enables you to look at a Sentinel-2 image from any date, and you can go through and watch the progression of a forest fire or a logging road, as well as, of course, the last observation that I'm showing here and that I've shown throughout the presentation, as well as some Landsat images. So I encourage you to check it out if you're interested in digging into the data more. And if you have any questions or feedback, I'd love to hear from you. Here's my email address, and we'll also, of course, have the Q&A at the end. So if you have questions, keep them in mind. And yeah, thank you all. And I'll pass it off now to back to Alice.
Thank you so much, Amy, for that in-depth overview of both of the GLAD systems and how they can be accessed and used. That was incredibly helpful. I'll actually now pass it over to Johannes to discuss the RADD alerts.
Thanks, Alice. Welcome, everybody. Oh, it's a bit of a... There we are. In the next roughly 50 minutes, I'll expand a bit on the new RADD forest disturbance alerts, the radar-based alerts. And I'm giving this presentation also on behalf of our team at Wageningen University. So there's really a bunch of people in our group that strongly supported the development of the new RADD alerts. You can see also the website, you find more information about the RADD alerts. So as mentioned before, the RADD alerts are a new forest disturbance alert that uses the cloud penetrating Sentinel-1 radar data. We also published a paper, whoever is interested in more technical detail and methods about the new alert system. It's actually a collaboration also with Global Forest Watch, Google, also UMD, so Amy also supported the work, European Space Agency, Deltaris, and it's really meant to not to compete, but as mentioned before, to really complement existing alert systems. So the CLAD, the Landsat-based, the Sentinel-2-based system, or also the JG4 system. At the moment, we cover the humid tropics of Africa, so primary humid tropics of Africa and insular Southeast Asia, and we're also on the way of expanding it to the pantropics. Here, an example of the RADD alerts and an animation of a logging road network in the Central African Republic, where we now are able to really track these changes consistently over time. So that is the advantage of radar sensor. It's not handled by cloud. So whenever we have an image, every 6 to 12 days, we can also see the change. So what we clearly see is that we see first roads being developed, and then in their direct surroundings, we detect effects of selective logging. There's actually a logging road network that has been active over the last 2 years. Sorry, there's a bit delay. Yeah, maybe going back, just don't want to talk too much about it, but we have started developing the RADD alerts in the Congo Basin because there was really a need, because the Congo Basin is probably, or in particular countries like Gabon, the most cloudiest in the world. And what we see here is actually the average number of Landsat observations, so not Sentinel-2 observations. There are more Sentinel-2 observations now, but a number of cloud-free Landsat observations per year. And we can see in red, this is below 1 cloud-free observation per year. So this is really areas that are persistently cloud covered. And that, of course, limits optical data or Landsat data to support law enforcement activities. This is also a lot mitigated with the new Sentinel-2 alerts. Another issue, and Amy also touched on that, is that actually the remote sensing signal itself disappears quickly, in particular if it comes to selective logging. So what we see here is a planet imagery of January, February, and March 2019. You can see a logging road developing in February and March, and you can see in September for the first time tree openings. So the result of selective logging. You can see in October, and in November it starts disappearing due to fast regrowth and canopy closure. So we need to be very quick in detecting these changes. How do we define forest disturbance? Very similar to the optical-based system as the complete or partial removal of tree cover in a 10-meter Sentinel-1 pixel. The complete removal is stand replacement. So you can imagine a pixel in the middle of the logging road, for example, and partial removal is often related to boundary pixels. So if you have something at the edge of a logging road, for example, or selective logging where only part of the pixel is damaged. We map disturbance within the boundary of primary humid forest, and we define primary humid forest by using the primary humid tropical forest mask for the year 2001, and we remove forest loss, annual tree cover loss from the Hansen data set, and we also remove mangroves. Now a few slides about Sentinel-1 and radar. So what is the difference actually between optical and radar? First of all, optical is passive remote sensing, meaning we reflect, acquire the reflection of the sunlight. So the sun basically illuminates the trees or on top of the cloud, and what we record is the reflection of the sunlight, similar to our eyes. So it's an active system. The satellite is actually nadir looking, so it's looking down. Radar satellites are a lot different. They're active satellites, meaning they use the antenna to actively transmit a wave of electromagnetic energy in the radar wavelength, so a much longer wavelength that travels through space. It can penetrate through most clouds and also can penetrate partly into the forest canopy, and we get a reflection, the so-called backscatter. We record whatever travels back to the antenna. That's what we record. So that's why radar is also more sensitive to the structure of the forest. Because of the long wavelengths, we are able to penetrate partly into the canopy, while with optical satellites, we get the reflectance from the top part of the canopy. About the ESA Sentinel-1 radar satellite, it's really a game changer if it comes to radar satellites, since for the first time we have dense and high spatial resolution radar observations available globally and freely. And that's a big change. It's a C-band radar system, so the wavelength is C-band. That also means it's not the most suitable wavelength for forest monitoring, actually. Something like L-band, something the Japanese ALOS pulsar satellite, for example, uses, it's much more useful for forest monitoring. Nevertheless, we are able to squeeze out a lot of information. The pixel spacing is 10 meters, and in the tropics, we have observations consistently every 6 to 12 days. You see here the coverage of areas with 6 days, 6-day coverage, and other areas that are at the moment only covered 12 days. It looks a bit random, but it basically comes down to tectonically active areas where we have 6-day coverage, because these are monitored for tectonic activities. So we see, for example, that most of the part of insular Southeast Asia is 6 days. Eastern Africa, Western Africa, a lot 6 days. The Congo Basin, a lot only 12 days. Peru is 6 days. A large part of the Amazon every 12 days. The disturbance detection algorithm, as we mentioned at the introduction slide, so the summary slide, it works very similar to the RADD alerts itself. So we first create historical image matrices showing the previous forest conditions. So we use 2 years of data to calculate statistical matrices. Then we pre-process every newly incoming Sentinel-1 image. And we apply a forest disturbance detection algorithm on it that calculates for us the forest disturbance probability. So the probability that a pixel is actually disturbed. We say that there is a likely disturbance if the disturbance probability is above 0.85. And similar to the RADD alerts, we build confidence with the time series. We don't do that with just a number of detections, but we do it actually in a probabilistic approach. So subsequent observations are used to iteratively update the forest disturbance probability and increase the confidence within a maximum of 90 days. And whenever the confidence goes above 0.975, we say it reached high confidence. We also have apply a minimal mapping unit of 0.1 hectare. That means 10 8-connected pixels. So it could also be a string of 10 pixels to reduce the effect of remaining noise in the data. We also conducted a validation of the results. We for changes larger than 0.2 hectare. We found a false detection rate for the Congo Basin of roughly 2% and omission error, so misdetection of roughly 5%. I also say that we mentioned that we use, once the first image detects the change, that we use subsequent images to build confidence. So, and we assessed how long it takes us for high confidence changes actually to reach this high confidence status once they are detected for the first time. And we can see actually that for roughly 80% of the changes, we reached that within a period of a month. Here are some examples of the RADD alerts for Africa. We see on the left side an example of selective logging. So it's again this network of logging roads and selective logging you've seen at the beginning. We can clearly see here the development over time. So we also map it, of course, over time. And you can see here the light colors is older disturbances and the red ones is the latest. In the middle, we see smallholder agriculture, actually the dominant driver of forest disturbances in the Congo Basin region, where communities cut forest to plant new crops. And we can see that that is usually something that really happens at the edge of remaining forests. And another major driver in Africa is mining, and we can see here these typical patterns of alluvial mining. Now a few more screenshots from examples. Here we can see selective logging networks in ROC. We can clearly see here all the density of the selective logging, and we can also see some indication of also the logging road networks and indication of selective logging. We can also see here at the edge of forest shifting cultivation, so smallholder agriculture. This is even more visible in DRC, where this is really by far the largest driver. We can see here is the city of Kisangani, and we can see here the remaining patches of forest, how this smallholder agriculture slowly eats itself into the remaining, into the remaining forest. Here's an example from PNG, some Papua New Guinea, also selective logging. And here an example of oil palm expansion and new road development. Here we see a new road development. Here, these big patches of new of forest clearings for oil palm in Borneo. And I would like to finish with an example of a logging road development in West Papua, which is impressive and scary at the same time. So it's impressive that we are able to detect these changes in such a high spatial and temporal detail now. But it's also scary to see the magnitude of forest loss in these areas. So in particular, West Papua and PNG is also called the new frontier of deforestation in Indonesia, while we see a decline of deforestation in areas like Borneo and Sumatra. I mean, Sumatra is not much left, but there should be now really a lot of attention on West Papua and Papua New Guinea. Limitations or less limitations, cautions when using the RADD alerts. So we also mentioned in the introduction slide that the systems itself are very similar, and that the differences are largely related to the characteristics of the sensors that are used. And I also mentioned that C-band radar is not the most useful sensor for forest monitoring because it's very sensitive to soil moisture. It has in the radar framework a relatively short wavelength, but more on this in the next couple of slides. For the detection timing, actually, there's a great timing for small-scale changes, such as logging roads, smallholder agriculture, because we make use of something called the radar shadow. Because radar is side-looking, and if you have at the edge of the forest, if there's a gap, we do not actually illuminate this area, and we get the shadow effect, so a very low value, and that results in a very high contrast to a stable forest, and that enables us to detect these changes very clearly and very rapidly. Where we actually have some time, where we may have some delay or even omission, is at bigger patches, because in these bigger patches, what we see here on the left side, it's not the best example, but maybe the example is better if you remember Amy was showing this image from Windthrow, where a lot of trees are like broken. In these areas, it's much harder for C-band to detect it because there's still a lot of forest structure present, and that forest structure looks very similar to the forest structure of stable forest. So the separation is more difficult. Also, sometimes after deforestation, what can lead to a delay of detection is if there was just a strong rain event, and that leads the soil to be very wet, and a very wet soil lets the radar signal to jump up to a level of stable forest and close to stable forest. So that is that may lead to some delay or omission. And that is that's, for example, areas where the Sentinel-2 alerts have very few problems. So a combination is very smart. Since radar is side looking, we also have more effects in topographic areas, and that can in some areas lead to less accurate detection in steep mountains. What we can see here, for example, is logging roads. You have an indication of the logging roads, but they are not fully connected. Nevertheless, you still see that there's a lot of activities going on. So again, if this is an area where something should not happen, then you know that you should go there and check. So even though not the full logging road is detected, we still indicate that changes happen. For potential force detection can happen in wetland areas due to the sensitivity of the C-band radar to moisture. So sometimes wetland dynamics in itself, they lead to a strong change in the radar signal, and that can lead to force detection. This is to a large part the result in the RADD alerts if it occurs due to the inconsistency of the forest baseline product. So what we use is the Hansen or the primary tropical forest mask, which is based on Landsat data. And what we see here is on the left side, actually, and clearly in wetland, a non-forested wetland area with high moisture dynamics. And this is the baseline product we are using. And we can see that there's a lot of areas that are actually not mapped. So non-tree covered wetlands that are not mapped. And in these areas, we may see some detections that are not true detections. So what I can suggest, if, for example, if you're from a national institution and you have a better forest mask available, you can just put it on top of the alerts or mask out these wetland areas. So use local or regional products. Another constraint from the baseline forest product is, of course, what I just mentioned. Number one is force detections areas where they are incorrectly labeled as primary forest, but also detection of changes prior to the start of the monitoring period. So, for example, in Peninsular Southeast Asia, we start monitoring in 2020. So our baseline product uses the 2001 primary tropical forest mask, and we remove all the annual loss for the years 2001 until 2019. However, the 2019 product, and that is well known, does not cover all changes in 2019. For example, in the last 3 months of the year, there might be a lot of cloud cover. So in the annual mosaics or composites that were used to actually map the change for 2019, these changes are not included. They will only be mapped in 2020. And in our product, since we use it as a baseline, we detect these changes at the beginning of the time series. Incorrectly of the date, of course, they are detected because the baseline product says there is still remaining forest at the beginning of the time series. This is not such a problem for the latest changes. This is really something that affects the first part of the period for which we provide the alerts, but just important to be aware. Data access, what we provide is 2 layers. One is layer of showing for every pixel, whether it is high confidence or confirmed or unconfirmed low confidence, and the timing of change. The data is available at Global Forest Watch for visualization, and soon it will also there will also be data download possible, and it will be available in Global Forest Watch Pro. You can find a lot of information about method updates and data access via Google Earth Engine at the RADD Alert website, and we also would like to advocate the RADD Alert app, and similar to the Sentinel-2 CLUD app, it provides an alternative ways of viewing it a little bit more, playing around with the data. Next steps, of course, we will keep further improving the alerts, the methods around them, and we expand to the pantropics. That will happen later this year. We are also working on improving the forest baseline mask we're using by integrating the Jedi Forest Height product. And what is maybe also interesting for some of you, we are currently working on an open source package for analysis ready Sentinel-1 data in Google Earth Engine that will be available very soon in the next couple of weeks. And I would actually conclude the Amy's and my presentation by coming back to the slide summarizing the 3 products. So the CLUD Landsat-based product, which covers the pantropics, the CLUD Sentinel-2 product, which is currently available for the Amazon basin, and the RADD Radar product, which is currently available for Africa and insular Southeast Asia. So that is the good news. These high resolution products already cover more or less the pantropics, but both the CLUD Sentinel-2 and the radar alerts will also expand to the pantropics. All 3 systems, the definition for forest disturbance are similar, if not more or less the same. All systems map all kinds of forest disturbances and do not separate humans from natural causes. So that is important. They do not make a separation between a wind throw or a meandering river, for example, from selective logging or smallholder agriculture. The methods that is employed is largely identical, and the difference in itself, they stem mainly from the characteristics of the different sensors itself. And with this, I would like to conclude my few slides. I'm super excited to receive questions at the end of the Q&A session, and please pass on ideas. We are very excited to collaborate. Here's my email if you want to reach out. And with this, I would like to give back the control to Alice.
Thank you so much, Johannes. That was a really helpful explanation of the RADD Alert system. And it was really interesting to learn more about how you went about measuring forest loss and your approach. I'd now like to pass it over to Michaela, who will briefly discuss the Viirs active fire alerts and summarize what we've discussed today.
Great. Thanks so much, Alice. So before I begin, I just want to note that, Amy and Johannes really are the architects of these alert systems. The Viirs alert system that I'm going to present about, I was not involved in the development, so just be aware of that, but I'll still try and give an overview of what I think is important to keep in mind. So the fire alerts that we have on Global Forest Watch are using the Viirs active fire alerts from NASA. So Viirs is the Visible Infrared Imaging Radiometer Suite instrument that's aboard 2 NASA satellites right now. And essentially, they're using information about the thermal brightness that they get from this sensor to detect where there are hotter and brighter events that are indicative of fires. So the fire alerts have a global coverage. They're picking up fires within 375 meter resolution pixels, so quite a bit coarser than the 2 products that we just discussed. But the nice thing is that these sensors are passing Earth every 12 hours, and so we get this really near real-time coverage about where fires are happening every place on Earth. And we also have this information available from 2012 onward. So a question that we get a lot at Global Forest Watch is about what the fire alerts are actually detecting, and what these pixels that we have on the map actually mean. So here's a diagram that NASA provides to explain a bit about this. And I think the really important thing to consider is that each of these fire alert points is just representing the center of the pixel where a fire has been detected. So, you know, if there's a small fire, that still is a single pixel. If we have two fires within the same pixel, that still shows up as just one center point. And if we have a large fire that it covers multiple different pixels, that's going to show up in these 4 different points. So with that in mind, you know, those points don't actually give us a good idea of how much area is burning because the actual fire event can be larger or smaller than that pixel size. We also know that different than the other systems that, you know, are tracking a change in a pixel and then following up on that over time, this system actually detects fires and will get a new point in that location every time that the satellite passes and detects a fire there. And so if there's a fire burning in the morning and there's still one there 12 hours later in the afternoon, we're going to pick them up as 2 separate pixels. So I think that's just a good thing to be aware of when you're using this data. In terms of the limitations, accuracy, one thing that's important to note is that the system is better at picking up fires that are larger and hotter. So this diagram here on the left is from the paper around this system. And essentially the line, everything above the line is what can be detected at least 50% of the time. And so things that are larger and hotter are going to be picked up easier than things that are cooler and smaller. There's also a difference between what can be detected during the day and at night. During the day, it's a bit harder to distinguish fire events from other places that might be bright or hot because of sun reflectance. And so during the night, actually, we can pick up even smaller and cooler fires than we can during the day. We also know that there are some omission errors with the fires, especially when there's heavy cloud cover or smoke. Also, sometimes when there's heavy tree canopy and the fires are burning underneath the canopy, they can be difficult to pick up. And so we might have omissions there as well. And then there are some commission errors as well, most typically during the day if there are areas of sun glint, where again, it shows as really bright and hot in the sensor, but it's actually just because of the reflectance. And so because of that, this product is actually separated into low, nominal, and high confidence fire alerts. And most of those commission errors are going to be in the low confidence. So you can separate out which level of confidence you want to see. As far as access, we do have the fire alerts, as I mentioned, on the Global Forest Watch map. We also feature quite a few statistics of these fire alerts on the Global Forest Watch dashboards. So I'm showing an example here, looking at the number of fire alerts that were detected over time compared to the mean and standard deviation from previous years to get a sense of what's normal or not normal. And then also, this is available on the NASA website. This is all part of their Fire Information Resource Management System firms. And so they have a website there where you can access the data, visualize it on a map, and download everything as well. So just to step back a bit, now that we've talked about all of these alert systems, I think it's really important to keep in mind why we're doing this and really what the purpose is of all of these systems. So really we think about near real-time alerts on Global Forest Watch as just the first step in a chain. So, you know, using satellite imagery to be able to detect where deforestation might be happening as quickly as possible is a really important piece of it. But then there needs to be this chain of action that follows and hopefully end up in some kind of result and change on the ground. So most often how this plays out, you know, we're detecting the systems, we're sharing them, making them available through Global Forest Watch and through other applications. But then there needs to be some kind of investigation to document what has happened, whether that's, you know, visiting the location in the field, flying a drone over, or analyzing high resolution imagery to understand what the drivers are, who might be responsible, whether or not it's illegal, the size of the damage, those kinds of questions. And then ultimately it relies on some kind of final step of, publicizing the alerts, reporting to the authorities, having some kind of government investigation. So some of the things that Alice mentioned at the beginning. And that's really, I think, where many of our users come in. Amy and Johannes and the other alert partners that we're working with are really doing this first step of detection. For Global Forest Watch, we're sharing the alerts and trying to make it easier to do this kind of response. But then really it's up to all of you and all of our users to make that final step and actually turn this information into something that's actionable and hopefully is going to result in fewer deforestation alerts down the line. So I think that also comes into play and is important to consider when you think about how to use this information and what we really built it for. So the purpose of these systems really is to show where deforestation might be happening, or fires in the case of the fire alerts, as quickly as possible. And it's really about a starting point for further investigating what is going on. And so we see this really as needing to be complemented with other additional information, which is something that we'll talk about in the second webinar in this series. High resolution planet images, for example, where you can determine the driver, information about the land ownership, if it's in a protected area. Those are all really critical pieces of information as well when thinking about alert information. And finally, we know that it's really critical to deliver this information as quickly as possible. And so try to do this through the Global Forest Watch email notification system. We can get an email anytime there's a new alert in your area of interest, and also through the Forest Watcher mobile application. Amy talked about this a little bit, but I also want to highlight that, these systems are really taking the latest available image to try and detect change as quickly as possible. And as a result, they're not necessarily built for reporting areas or trying to assess trends over time. We have other products like the annual tree cover loss that are a bit more adapted to doing that and use much more information to assess those trends rather than these alert systems that are really trying to pick up change as quickly as possible. Overall, though, I'm really excited about these new alert developments that you all just heard of. We've had the GLAD alerts up on Global Forest Watch for 5 years now, I think, and have gotten a lot of feedback over time and requests of how we can improve. And so I think the GLAD S2 alerts and the RADD alerts that you just heard about are going to be really important for solving some of those problems that we heard earlier. And so, as you heard, having this higher resolution where we can detect smaller changes and selective logging, being able to use the more frequent revisit time and the radar images that can penetrate clouds to actually detect changes faster and not have as many of the delays as we've had with previous systems. And I think also having this increased reliability from having more than one system running. Certainly there have been times when, the Landsat data pipeline will go down for a couple of weeks. And now we actually have these other systems that can fill the gap if something like that happens. So thinking ahead to what our next steps are as Global Forest Watch about these alert types, definitely adding these new alert systems to the Global Forest Watch ecosystem. So they're already on the Global Forest Watch map, but we're working on adding them to the email notifications, to the Forest Watcher mobile app, to Global Forest Watch Pro and some of our other applications as well. So they have the full functionality of the GLAD alerts that is available right now. So we'll talk more about that in the second webinar in this series. As you also heard, we are working to expand both of these systems across the entire tropics, so having them running at a pan-tropical level. And I think that really raises the question of how we can make these better accessible and better integrated with each other. As you heard, there are different strengths and weaknesses of each of these systems. And so I think really combining all of them together is going to make a much stronger product than either one alone. And so we'll be working over the next few months and over the next couple of years, really to integrate these systems on Global Forest Watch so that you can get the best of all of these systems and not necessarily having to choose which one you want to use. Because really we do see these as complementary products that can reinforce each other and give more confidence and faster detections than any one of them alone. So overall, I think there's a lot of work to be done still, and really excited about the developments that we have in these new systems. And as Amy and Johannes said, we're really keen with these new systems to get your feedback, to hear about how you're using them. So please don't hesitate to get in touch with us, and we'd love to hear what you think. And with that, I will pass it back to Alice.
Great, thank you, Michaela, for a great introduction to the Viirs alerts and summary of all of the alert systems we've discussed today. Before getting to the Q&A, I'll just quickly conclude with an overview of the Global Forest Watch Help Center. Just one moment, please. So to find additional information on how to use Global Forest Watch to monitor forest change, please visit the Global Forest Watch Help Center at globalforestwatch.org/help. There you'll find step-by-step tutorials, webinar recordings, frequently asked questions, and other resources that can help guide you through the Global Forest Watch tools and the data that they feature, such as these alert systems. And as a reminder, we'll send a copy of this presentation that have all of the links attached alongside a recording of this webinar in the next few business days. So now moving on, we'll get into the Q&A. So in the Q&A, I was seeing a big theme of questions about coverage and where the different alert systems are currently available and what the plans are for expanding the coverage of the alert systems, as well as if there's a plan to expand beyond the tropics, so into boreal forests and different types of forests. So perhaps Amy and Johannes, do you want to take on that question regarding your two different alert systems?
Go ahead, Amy.
Oh, sorry. Can you go first? I was looking at, yeah, I got a little distracted.
I can answer. The question was whether about the expansion of the systems also to other geography and not just within the tropics, but also outside the tropics. And purely for the humid tropics, for the RADD alerts, we are planning to expand them within the next couple of months to the remaining pantropics. We're also working, and there was also a question on expanding them to the Triforest, so also stay tuned about that. And of course, since there is a lot of attention on around the new European Green Deal, there's a lot of attention also illegal, unsustainable forest practices in Europe. There's also research ongoing to convert some of these concepts to more the Northern Hemisphere, but not on an operational scale within the next, not soon at an operational level. And there was also a question before I passed to Amy on why, that links to that, why Triforest is more difficult to monitor. And that is because the dynamics, the normal behavior. So what we do is also we have these matrices of historical data that show what are the normal behavior of the forest. In the humid tropics, there is not a lot of seasonality of that signal. So it does not change a lot throughout the year because it's like evergreen moist forest. While in Triforest, there's a lot of change throughout the year, and that normal seasonality can interfere a lot with actual change. There is ways to model that seasonality, but it's not so straightforward. That's also why there's always the tendency, of course, we can do it, but usually the accuracies in Triforest are not as good as in evergreen forest. Yeah, and with that, I would like to pass to Amy.
Yeah, so yeah, definitely the same thing applies to the dry forest with both the Landsat and the Sentinel. But yeah, so we're hoping to have the Sentinel-2 expand pantropically by the end of the year. So we'll see what issues we'll come into as we do that. But that should be manageable to have that out by the end of the year. As for yeah, there's definitely interest in doing things globally, and we are exploring a little bit of some other change dynamics, and we do have the Landsat global annual map, but being able to have the whole year's worth of data, particularly when you are dealing with trees that lose their leaves and all kinds of different dynamics like that, it is really helpful to have the entire year. We have discussed the possibility of having a global alert sometime in the future, but along with Johannes, it's not something that's in the works yet, and so that would be a longer time coming.
Thank you both. That was really helpful. So another theme that I'm seeing across the questions is whether these alert systems are available for download, and if so, where?
Yeah, so you can download both the Sentinel-2 and the Landsat from the GLAD web pages. You can then get the raster data. You can download the Landsat alert also in a different format from GFW directly. And the links for those you can all find if you go on GFW and go to more information on the alerts. You can find the links to all the different source data pages where you can where they'll have the downloads both for the GLAD products as well as for the RADD product. I'm pretty sure you can, Johannes, you can confirm that maybe.
You can't download them as a GeoTIFF at the moment, so that is something that's under construction at the Global Forest Watch site, but their alerts are available for access via also Google Earth Engine, and you can just download them from there. So it's just one step. I mean, they're available as an open asset in Google Earth Engine, and on the RADD website, where you also find the link in the slides, but also if you go on the Global Forest Watch website under metadata, you can also find the link to the website, and that's where we also show how to actually access the asset in Google Earth Engine, and from there you can download them. So all three data sets are already available freely for access.
Thank you both. And as a reminder, we'll be sharing a copy of the presentation that includes all of the links that were mentioned with you in the next couple of business days. So you'll be able to access those Google Earth Engine links directly from the presentation. So the next question is for Michaela. And the question is, do these images and alerts go directly to policymakers, or do you rely on someone else to pass it on in order to drive impact?
Yeah, that's a good question. So thinking back to that flow diagram that I showed of, the typical kind of process, we generally think of our role at Global Forest Watch as providing the information as openly and hopefully as usefully as possible. But it really does depend on our partners and users of the site to get to those next concrete steps. So we definitely do have partnerships with a number of different government agencies, with private companies, with organizations, communities on the ground that, we provide some additional support and trainings to, but also, we are trying to make this as open as possible so that anybody can use it even without our support and be able to make some kind of change.
Thanks, Michaela. So the next question is for Amy, and I'm actually going to piggyback it with another question. So the question is, how can you differentiate the forest disturbance caused by fire or other kind of clearings in the different GLAD systems? And then the question I'm going to add to that is, how can you use these data sets to distinguish between human-caused deforestation and other more natural forest cover loss, such as fires or natural disasters?
All right, yeah. Can I share my screen? Is that okay?
Go for it.
So I pulled up an example here. So here's a forest fire, and it can be. This is a good question. How do we distinguish these things? This is in Brazil, near Xingu. But one of the distinctive things about fires is we often have these rings, not always, but the day and night burning. But so if you can look at the actual alert or the data, it can be really helpful where you can then see this pattern, right? Also in the image. So these are a little more difficult. It's not an immediate thing from the alert. You're not going to get an email with like if you're subscribed to your area and the list of alerts, you're not going to get be able to immediately tell it's a fire. But if you can look at the alerts themselves, and particularly the images behind it, it can be helpful. This is an interesting case where you can see the road was built first and then the fire escaped out from there. But yeah, to the other question about, how do we distinguish between natural and otherwise? It is a difficult thing. And I mean, I think, right, some of it, again, is looking at the image. So in this case, we have these nice, clean, straight lines. Nature doesn't work in straight lines. So these then are logging roads, or well, not logging. This is probably for creating new agricultural areas, but that would be then a human caused. Some of the other things like the wind blowdowns are much harder to identify as such. But like this kind of diffuse pattern here actually, and if we click on it, it's this like really diffuse kind of it's not just like a regular pattern of selective logging. So it is a more difficult thing to try and assess. But yeah, so with all of these, I would encourage you to look at the imagery. I know that requires more data, more effort. But yeah, that's the best answer we can give you. Ideally down the road, right, maybe we would be able to give better indications of drivers. But at this point, it's a per pixel thing. And then the context is more by the user. So I will stop sharing unless you had another question along these lines. I have a couple other examples of, there's some logging questions too.
Amy, I didn't see the specific logging questions, but oh, here we go. Have you identified any significant areas of forest loss and intact forest landscapes that are a result of selective logging of certified timber, or has any correlation been drawn? So I don't know if we need to get into the specifics of that, but do you want to touch on that question?
Yeah, I mean, so this one, maybe even Michaela might be better suited to address in terms of being much more aware of all the different protected areas and the certification kind of things. Do you want to take a stab at that one, Michaela?
Sure, yeah, I can. I don't have any specific examples off the top of my head. I think, throughout the presentation, we've shown a number of different logging roads that come out very clearly in these new alert systems with the higher resolution. But definitely that question of, whether or not that's allowed is a different question. So currently with Global Forest Watch, we have a system called Places to Watch, using the current Landsat-based GLAD alerts, where we're looking at where those overlap with intact forest landscapes and protected areas to try and find, some of these most, I guess, egregious examples of deforestation alerts. So definitely are going to be working to integrate the Sentinel-2 alerts and the RADD alerts that, pick up these kind of logging signals much better into that system, so that we'll hopefully have a kind of systematic process for looking through these kinds of examples.
Thank you, Michaela, and thanks, Amy. So the next question I will point to Johannes. Regarding the RADD alerts, was the validation done on the ground or through high resolution satellite imagery? And in the case of it being done with satellite imagery, can there still be drawbacks of high resolution imagery over local ground validation, or vice versa?
Yeah, I mean, good question. We used mainly, high resolution Google imagery, and planet imagery, which is like 3.7 meters. And that is something also we explained in the paper and something also we put on the website. So there's, and that is, you get to with 10 meter already, because it's not always stand replacement. So that the entire pixel has changed, but also part of this pixel only changed. So you're getting into spatial scales where it's very difficult, even with this high resolution data, to on a pixel level to assess the changes and to validate them. So this gets very challenging, and that's why spatial context, that has been just mentioned before, is essential. So seeing, for example, a few pixels next to a logging road, this is very likely related to, it's like very likely selective logging or something. But having a few of these pixels in the middle of nowhere, it's sometimes very hard to validate these, and that's where real ground truth data is very useful. There's still a great value for them, but for our purpose, for doing a validation across the Congo Basin, it's also very difficult to access ground-based data that also coincides temporally with the alerts. So it's often that there is a lot of field campaigns from the past, but they don't help us so much to validate latest changes. And that's where the planet data, for example, is very useful. And I'm very happy to see that now the planet data mosaics are also available at Global Forest Watch. So that is a very useful data source to interpret the results. So having both in combination, the different alert systems and the planet data, and spending some time on actually looking at them and trying to understand what we see, that you can sharpen your eye a lot. And that's, I think, where the next workshop also focus at. But I would also like to share my screen, one slide that I showed in the, if you don't mind, in the presentation, is this slide, because you asked whether you are able to separate between different drivers. By practicing a bit, it is, for many changes, not so difficult to separate key drivers. For example, here, this is very clearly a logging road network, where you see like small agriculture is often these small patches of changes at the edges of forest, very typical. And also mining patches are often look a lot different in terms of scale and everything from smallholder agriculture and selective logging. So by being guided maybe through the next webinar and looking at different changes, the eye is a very good classifier that is able to, and then maybe in combination with the planet data, that is for many cases be able to separate these different drivers visually, to some extent at least.
Thanks, Johannes. That was really helpful. So we have time for one more question. And that question is, what is the smallest size of forest that can be detected when there is a disturbance with these alert systems? And can the logging of a single tree be detected?
Yeah, so I'll share my screen again. All right, so here's an example, right, of the alert. Here's the Google pre-disturbance that's there. And so you can see, right, we are detecting a whole lot of different things here. We can click on it and then see the most recent, and you can see there's a whole patchwork here, and we're definitely not capturing all of the trees that are being lost. And so certainly we're missing plenty. But we'll capture some. Here's the example I showed in the presentation, right? And you can see that there's clearly is trees that are being missed that you can even see in the Sentinel that aren't being captured. If you go around your territory and you see, oh, all these trees are gone and they weren't detected, that is going to happen. If it's a really big tree, sometimes we will capture it. So it is kind of, you have a give and a take where, yeah, some of that will be captured and some of it won't if it's a single tree. And with the minimum size, right? So for the highest confidence, we allow even a single pixel. So that's 10 meters by 10 meters. So it's a very small area. For the other confidence levels, there has to be, same as the RADD alert, 10 connected pixels. And then it's even larger for the first detection. So yeah, here's just a couple examples to try and clarify those questions. But yeah, we're not going to get every tree. Maybe someday. Maybe not everyone even wants that though. But I'll pass it off to Johannes.
Yeah, it is more or less the same. I mean, yes and no would be the answer. I mean, for some cases, you detect individual trees, if they affect the 1 pixel enough, but in other cases, you don't. And that's what I always said around these logging roads. That's why I also would say it's not, each individual tree's indication for selective logging. So we detect some of these openings or disturbances. Radars doesn't necessarily always need to be an opening, but the disturbance. And some of them not. So this is, well, it's exactly the same message that Amy conveyed. It also applies to the RADD alerts.
Thank you both. And thank you everyone for joining us today. I'm going to share my screen one last time. So we will be holding a second webinar in this kind of mini series, which will be intended to demo how you can access and start to investigate these alert systems on Global Forest Watch using the satellite imagery resources that are available. It's being planned for this summer and will be announced via our communication channels, so through our newsletter and through our social media channels. So please keep an eye out for that. And if we weren't able to get to your question, I know there are a lot of questions today, or if you think of an additional question that you want to ask one of us, please feel free to reach out to the Global Forest Watch team at gfw@wri.org or to Johannes and Amy. Again, we'll be sharing this presentation with you all in the next few business days, which includes our email, so you'll be able to reach out with any questions. Once we end this presentation, a survey will populate on your screen where you'll be able to share any feedback you might have on Global Forest Watch, on the data, or on the webinar. And this is really helpful for us, so we can ensure that these things are as useful as possible for you. So we appreciate any feedback you'd be open to sharing with us. So thank you, Michaela, Johannes, and Amy for presenting today. We really appreciated your time, and thank you, everyone. Have a great day or night or morning, wherever you are.